So the start of Biochem 2 really was a one-day sort of preliminary learning unit reviewing and overviewing concepts from Biochem 1 that we needed to know to move forward with Biochem 2. And so we kind of focus on biological molecules, biological processes, and then thinking about metabolism. So we had a pretty detailed worksheet that you guys worked through with me, which is the same content that's here, but I just wanted to take a minute and we could go through and kind of highlight what some of this information is. So again, some numbers to make sure that you know: physiological pH and physiological temperature. So again, we haven't had any information to indicate that pH would be any different, but I guess there's been some recent data that's come out to indicate that physiological temperature might actually be a little bit less than 37, more like 36.4. Actually, a really interesting article if you're interested in thinking about it more, kind of talking about the fact that we actually don't expose our body to too much of the foreign microbial world that's out there. So our immune system isn't as primed, and we don't need to have as high of a body temperature. So kind of an interesting theory there based on some factual data. So if you put 36.6, I'm fine with that. If you put 37, I'm okay. But no numbers that I want you to know nonetheless. Again, thinking about determining protonation states. So for any molecule that I might give you, based on pKa's that you need to know for some basic functional groups, and given a certain pH value, you should be able to draw what that protonation state looks like. So again, some pretty basic stuff there from Biochem 1. Thinking about the intermolecular forces we have, remember we had that hierarchy of 4 intermolecular forces. So nonpolar interactions, London dispersion forces, dipole-dipole interactions, hydrogen bonding, and then ionic interactions. So being able to identify those, not only by name, but thinking about functional groups that might participate. Defining the hydrophobic effect. So again, the tendency of nonpolar substances to minimize their contact with water. Lots of applications of this. We can use it to describe why proteins fold and put nonpolar amino acids in the interior. We can use it to describe why micelles form or why lipid bilayers form. So a lot of applications of kind of a basic definition for the hydrophobic effect. Lots and lots of times we are going to be thinking about kinase and phosphatase activity, kind of putting us in either a phospho or a diphospho state, kind of thinking about the 3 amino acids that can be decorated with phosphate. So serine, threonine, and tyrosine. So lots of regulation. Most of the metabolic pathways that we're going to learn about have sort of a regulatory component to them, and covalent modification is a very important piece of that. So again, knowing that kinases add phosphates, phosphatases remove them. Here are the 3 amino acids that we either add or remove phosphates from. Knowing that a fed state is really a diphospho system, and then a glucose or energy need state is a phospho system. So kind of some basic things to think about covalent modification for enzyme regulation. Again, some basic thermodynamics, thinking about entropy, enthalpy, and free energy. So know the letters that we know to describe each of these. Describing them in one word, entropy can be thought of as disorder. We think about heat for enthalpy and spontaneity for free energy. With entropy, the phrase that we want to think about is more molecules moving more, and for enthalpy, we want to think about bonds and intermolecular forces. Favorable entropy processes are positive, enthalpy processes are negative, and free energy is going to be negative for a spontaneous process. We talked about the 2 equations that allow us to think about free energy. One that implies or has to do with both enthalpy and entropy contributions to a spontaneous process. So again, the sign of this can allow us to think about whether a process happens. And then for delta G, with our delta G equals minus RT ln of KEQ equation, that can allow us to think about how much, again, because an equilibrium constant is a ratio of concentrations. Important to be able to think about our 3 main fuels. Most of Biochem 2 is going to be talking about the metabolism of these 3 fuels. First, thinking about the entire process of cellular respiration with carbohydrates, and then mapping it onto lipids and proteins. So being able to think about their caloric value, Again, both carbohydrates and proteins being worth 4 calories per gram. Lipids being nature's favorite storage, specifically as triglycerides, is going to be worth significantly more, 9 calories per gram. Thinking about the atoms that are there are going to be important when we think about how we break these down. So again, the main atoms that we think about for carbohydrates are carbon, hydrogen, and oxygen. Remembering that the empirical formula for all monosaccharides is CH2O, which is why they're called carbohydrates. I thought they were hydrated versions of carbon. For lipids, even though, yes, in fatty acids there are 2 oxygen atoms, for the most part it's just carbon and hydrogen, so fairly reduced, which is again why they're worth so much more. And then for proteins, we not only have our carbon skeleton, which is carbon, hydrogen, and oxygen, but all proteins comprised of amino acids have nitrogen, and that's an important atom that we need to think about sort of eliminating, and so we'll talk about the urea cycle. And then if we're talking about some amino acids like methionine or cysteine, we also have sulfur to consider. Being able to think about how we polymerize these monomers, we talk about their linkages, right? So it's a glycosidic bond that links carbohydrate monomers together to make polymers. Peptide linkages or amide bonds are going to link amino acids together to make proteins. And then even though it's not a polymer per se, we want to think about an ester linkage that hooks these fatty acids onto a glycerol backbone. So again, naming what those monomers are: monosaccharides linked via glycosidic bonds, fatty acids linked to a glycerol backbone via an ester linkage, and then amino acids linked via a peptide or amide bond to make proteins. So importantly, being able to draw any of these biological molecules. So again, for proteins, we talked about and we took some time to physically sort of draw these out together. Lots of different words that I can ask you to draw out for proteins. So for example, when we learned how to draw a protein or reviewed how to draw a protein, I like to draw my NC-alpha carbonyl, NC-alpha carbonyl, NC-alpha carbonyl. I like to draw my peptide backbone first. Again, my N terminus is going to be protonated. My C terminus is going to be deprotonated based on the pKa's of those functional groups. I like to then take and write the letters for the amino acids that I need to put in underneath where my alpha carbon is. And so I can see where all my alpha carbons are here. I'm writing the amino acids that are there and then being able to draw in the amino acids that we have here. Now I highlighted when we did this that at this point in the course you do not need to know the exact structures, but again, given a list of the amino acids, not saying what they are, but just a list of the structures, knowing, oh yeah, this is histidine, I'm going to throw that guy in there. Knowing that proline, for example, is one of those unique amino acids where the backbone kind of ties back into the side chain. And so being able to draw a peptide is important. Identifying again these peptide bonds, which is where we're going to have either linkages that are broken or created if we're talking about catabolic or anabolic processes. Lipids. So again, with lipids, specifically we're talking about triglycerides. So begin by drawing a glycerol backbone. Again, if it was glycerol, these would be OH groups here. But because we esterify a fatty acid with a carboxylic acid functional group to make our triglycerides, we generate our ester linkage here. And so you can draw a triglyceride basically by imagining there being not a hydrogen here, but we're going to have a carbonyl, so we can have our ester linkage. And then we're going to draw out our fatty acid tails. Now, based on the information that's given to you by what fatty acids you have to draw, I'm fine with you drawing everything in the trans configuration because it's just way too hard to think about drawing them as a cis configuration. They end up kind of looking like caterpillars or something kind of curling around here. So be able to identify where double bonds might be, again, based on whether we tell that it's an omega-6 or an omega-3 fatty acid. So again, omega-6 fatty acids means that at the 6th carbon in from the end, we're going to have our first double bond. Omega-3, we come in 3 carbons from the end. Again, be able to recognize that those are going to be double bonds in the cis configuration. Some important information to think about when we do have additional double bonds, if we're going to have a polyunsaturated fatty acid. 2 rules that we have to adhere to. Double bonds are never drawn in conjugation, and they're never going to be before carbon 9, remembering that our highest priority functional group here with our ester, this is carbon 1. So just some rules to think about being able to draw any fatty acid. So carbohydrates, the main one that you have to draw is glucose. So be able to draw a Hayworth projection of beta-T glucose, which is nature's favorite. The beta, remember, is because these two groups are on the same side. They're both on the same side. So the exocyclic CH2OH group, H group, and the anomeric carbons OH group are both pointing in the same direction. That's what makes it beta. For glucose, it's easy to draw because we are going to alternate our bulky groups, and that's why it's nature's favorite, because we can have all of these substituents being equatorial. Once you can draw glucose, then it's going to be easy to draw any of the other structures that we might need to think about. For example, galactose is a C4 epimer, so we'd switch the hydrogen in the OH group at this position. Mannose is a C2 epimer, so we'd switch these guys. Now again, this is beta-D glucose in a pyranose structure, so a 6-membered ring. Remember, there are some sugars that exist as a furanose ring or a 5-membered ring. So again, this carbon by formalism is going to be the anomeric, or the number 1 carbon. But beta-D glucose is what I want you to be able to draw. Nucleic acids, like we think about with peptides, we want to draw the backbone first. So I like to think about drawing a backbone. Start by drawing an OH group here. It could end up that there might be some phosphorylation that we have at that. In this case, it is 3' phosphorylated, not 5', so this is going to be an OH group. Then we draw our C6 exocyclic group here, and then we draw a 5-membered ring to generate our ribose ring here. This tells us that it is a nucleic acid. So again, nucleic acid and ribonucleic acid are generally synonymous, so this tells us it's RNA, so we're going to have an OH group at the 2' position. In general, I've told you you don't need to worry about drawing the structures of the bases, but you do need to show where they attach. So again, this is our first residue. Then we need to draw the phosphodiester linkage. So we're going to have an oxygen from our 3' hydroxyl, then we're going to have our phosphate group, and now we're back to where we're repeating. So again, this is the same oxygen like we have here, and so we're going to repeat. Exocyclic C6 group, we're going to have our 5-membered ring here for our ribose, and then we're going to have our base attached there. Again, as a nucleic acid or ribonucleic acid, it's going to have OH groups, and then again, this could be an OH group on our 3' position, but this tells us that it's 3' phosphorylated, so we are going to put a phosphate group at that position. Again, 5' to 3' is the direction that we tend to draw our nucleic acids, or at least that we're going to be naming them. So again, labeling our 5' and our 3' positions and showing directionality is important. Phosphodiester bond tends to refer to both of these bonds here, so you can kind of highlight both of those, or kind of identify that this group is really the phosphodiester linkage. So a couple of things to highlight. If it was a deoxyribonucleic acid, then this would be a hydrogen rather than an OH group, because we'd have DNA rather than RNA. So those are the 4 structures you need to be able to draw and think about from kind of reviewing from Biochem 1. Reaction mechanisms. We really didn't do too much in class here to review. If you need to, go back and kind of revisit the reaction mechanisms in all of the videos from Biochem 1. Some things to highlight, some common chemistry that we're going to see, is remembering that carbonyl containing functional groups have a carbonyl atom that is a decent electrophile, and then adjacent to that carbonyl group, the alpha carbon tends to have a hydrogen atom that can be acidic, because we can resonance stabilize that conjugate base through that carbonyl oxygen atom. So not going to say too much here with reaction mechanisms. If reaction mechanisms is something you need to review, all of those videos are back in our Biochem 1 Blackboard site. Thinking about reaction coordinates, again, an important thing to think about as we think about particularly enzyme chemistry. So reaction coordinates are drawn by drawing energy on the y-axis and reaction progress on the x-axis. We always show the conversion of reactants to products. In this case, we're showing an exergonic reaction. Again, since we're showing free energy here, this is going to be referred to as exergonic because energy is given off. We're going downhill in energy. Again, deltas are always represented as differences Products minus reactants, final minus initial. Since we have a smaller number minus a larger number, that means this process is negative. That's going to be favorable. We already knew that from our thermodynamics table. Negative free energies represent favorable processes. So when we think about delta G, the sign of delta G again tells us whether a process happens. Again, negative meaning it's favorable, so it does happen. The number that might be associated with delta G represents the magnitude, and that is related again to how much. That's that other equation, delta G equals minus RT times the ln of KEQ, relating an equilibrium constant to amounts. So that's delta G, and again, that's whether and how much. When we think about connecting the energy levels between reactant and product, we always go uphill and proceed through a transition state. The difference between the reactant and the transition state next to it is delta G double dagger, and that reflects how fast a reaction is. The height of the hill being very large is going to represent a slow reaction because there's going to be a lot of energy that it would take to come up and over this hill. So again, the frequency that a molecule will have enough energy to have that happen is small, so it happens infrequently, making for a slow reaction converting reactant to product. So the last thing to sort of map on here is how enzymes work. Enzymes work by lowering the transition state, and that by its nature makes delta G double dagger smaller, and so it makes a reaction faster. Some important things to remember with enzyme chemistry: we do not change delta G, so we do not change the energy level between reactants and products, which also means we don't change whether a process happens. We don't take a non-spontaneous process and make it spontaneous. We also don't change how much product we make. All we do with enzyme catalyzed reactions is just get to that same predetermined amount of product at a faster rate. So kind of putting some things together here with some important either equations or models that were important for us to study. We studied the Peretz model or equation to think about hemoglobin and oxygen delivery. So an equation that we made up reminded us that the deoxy state of hemoglobin, which is the T state, is not bound to oxygen, but rather we think about it being bound to protons. To highlight again, this is not saying that oxygen and protons bind in the same spot, but it's reminding us that these are mutually exclusive, so that the deoxy state of hemoglobin, which is not bound to oxygen, is protonated. And then again, when we bind oxygen, that means we release protons. So two things to think about, and there was lots of ways that we talked about manipulating this equilibrium. But again, when we think about being in a high oxygen environment, so for example in the lungs, when we're binding oxygen, high concentration of oxygen is going to push on this equilibrium, it's going to shift it to the right, and again we're going to have more of our hemoglobin that's in its oxygenated or R state form. Conversely, we talked about what happens when you're in either a state of metabolic or respiratory acidosis. Again, being in a state where you are producing a lot of protons, for example, doing a lot of cellular respiration, a lot of ATP hydrolysis, that's going to increase the concentration of H+. A push on this side of this equilibrium is going to shift the equilibrium to the left. It's going to put more of hemoglobin in its T state, meaning that it's going to release its oxygen, allowing more to be delivered to the tissues that need it. We also had an equation that we started out very simply with at the beginning of Biochem 1, but then gradually mapped on the entirety of our metabolic pathways on here. So again, fuel is oxidized to ultimately generate carbon dioxide, water, and energy. That was kind of the basic equation we started out with. But now we understand more fully that fuel, when it's metabolized, is oxidized. Those electrons that are lost are harvested by our two B vitamins, NAD+ and FAD, as vitamin B2 as FAD and vitamin B3 as NAD+. These cofactors are then reduced to NADH and FADH2. They're shuttled to the mitochondria, where they undergo delivery of their electrons to the electron transport chain. So again, those species being oxidized allows them to be regenerated and reused. The electrons then go on to the electron transport chain. As the electrons make their way through the electron transport chain, chemistry happens to allow for the synthesis of a proton gradient. That proton gradient is then dissipated to generate ATP in a process that we know as oxidative phosphorylation. and that is the nature of the energy that's produced. So as these electrons finish their circuit through the electron transport chain, they are delivered to the final acceptor in the electron transport chain, which is oxygen. As oxygen receives these electrons and itself is reduced, that's how we generate water in this process. And the last piece of this equation is understanding that when fuel loses its electron and becomes fully oxidized, that's how we generate CO2. And as we go through Biochem 2, we're going to learn all the places where CO2 is generated, where water is generated, and importantly, where we generate ATP. Michaelis Menten equation, just the last thing to kind of remind us that a lot of times we are going to be talking about reaction rates of important enzymes. So we do want to remember what the Michaelis Menten equation is. So V naught, which is the initial reaction velocity, is equal to Vmax, which is the maximum velocity, times the substrate concentration, over Km plus the substrate concentration. So importantly, Km we can think about as the enzyme's affinity for substrate, or thought of another way, it's the substrate concentration you need to be at in order for the reaction velocity to be half of its maximum. So these tend to be two important kinetics parameters we'd like to know about. So again, Vmax and Km is what we want to know, but what we're able to measure are things like the initial reaction velocity and substrate concentration. So again, how we fit data that we can measure to get data that we want to know, like Km and Vmax, is all about sort of analyzing kinetics data. We use sort of the very simple method of the Lineweaver-Burke plot, which has its pluses and minuses, but there's lots of different ways to basically fit this data to give the kinetics parameters that we're interested in. So a lot of information kind of thrown at you to summarize some important concepts from Biochem 1, but I promise you the reason that I'm having you learn these is because they are going to come back and be revisited in Biochem 2.